I hope you like geometry because we are about to do some. First question, if you are standing 6 feet away from a mirror, how far does your reflection appear to be? So if you remember in the previous video with a flat mirror, like so, the object distance equals the image distance. So the object in this case is you, and the image is your reflection over here. And so if the object distance is 6 feet, the image distance is also 6 feet. But the question is, how far does your reflection appear to be? These distances listed here are the distances from the mirror. So if this is 6 feet and this is 6 feet, then your reflection appears to be 12 feet away. There you go. It's an ugly 12, but you get the idea. Next question. If you are standing in front of a mirror, you can see a variety of rays that bounce off that mirror, and the ray that bounces off the very bottom of the mirror here represents the closest point to the mirror on the ground that you can see. Because if you look up a little bit here, that's going to bounce off at a higher angle, and you're going to be able to see this location here. So the question is, what is this distance? What is the nearest distance to the mirror that you can see in the bottom of the mirror given these dimensions? So first of all, if we think about the level of our eyes here, so we draw out a line, and then we look at this distance here, that's going to be the 1.68 from the ground to our eyes minus 43 centimeters, or 0.43 meters, and that is going to give us 1.25 meters from the bottom of the mirror to the level of our eyes. Once we've got that figured out, I'm going to redraw this over here just to make it clear. I'll draw that a little bigger, and we have something, ooh, bad triangle there, sorry. We have something that looks like this, and I guess that image is probably better. So this distance here is 0.43. This is 1.25. This is 2.8, not drawn to scale. And we want to find this distance here. The law of reflection tells us that these two angles here are equal. Technically, the law of reflection says these angles here with respect to the normal are equal, but that is obviously going to make these two angles here equal. Now, if those guys are equal and these are both right triangles, that means we have similar triangles, so we can set up a ratio. We can say 2.8 is to 1.25, as x is to 0.43. That's how similar triangles work. As long as you have the sides opposite the same angles, then the ratios between those sides will match the ratio between the other sides of a triangle that has the same angles. So now we're going to multiply, cross multiply and divide. So x equals 2.8 times 0.43 divided by 1.25, and that gives us approximately 0.96 meters. So a little bit of geometry there. Hopefully you haven't forgotten all of your geometry. Alright, last problem. Let's say that we know a bunch of information about the sun and the moon. We know their diameters, and we know the distance to the moon, and we want to find the distance to the sun. We're also given this nice gem of information here, that the disks of the sun and the moon are about the same size in our sky. That is actually true. That's why we can get a full solar eclipse, a total solar eclipse. The size of the moon in the sky does vary a bit because the distance to the moon varies a bit. That's why sometimes, even though the moon is right in front of the sun, you don't get a total solar eclipse. You get what's called an annular solar eclipse. That happened a couple years back here. Anyway, if we assume that they are matching up nicely, then we can draw Here's the eye of our observer on Earth, and they are gazing out, and they see the moon as they gaze out. And then if there was an eclipse, right behind the moon would be the sun, but even if they're not lined up, we know that they have the same angle from the edges to our eye, because that's why the disks are the same size in the sky. So this allows us to also have similar triangles. This angle is obviously the same between this triangle here and between, make our eye a triangle, between that triangle and the larger triangle made with the sun. So these angles are the same, obviously, and that angle is the same, so we have similar triangles. This distance here is 3,475 kilometers. This distance here is 1,392,000 kilometers. So once again, not to scale, but that's okay. We have the distance to the moon, 384,400 kilometers, and that is from here to here. And we want to find the distance to the sun, so the total distance from here all the way over there. That's what we're looking to find. So similar triangles are really nice. For instance, if the sun were exactly twice the size as the moon, twice the diameter, and they're the same, they appear the same size in the sky, then we would know that the sun is exactly twice the distance. Well, it's significantly more than twice. I think the one on my million here went away. It's significantly more than twice the size, so it's going to be significantly more than twice the distance, and we can find this again by setting up a ratio. So if I have 384,400 is to 3,475, I can set that equal to my unknown, the distance to the sun, over 1,392,000. Okay, again we'll cross multiply and divide, and we solve for the distance to the sun. Works out to be about 154 million kilometers is our nice rough estimate. The actual distance is 149,600,000. So in the ballpark. And there you have it. Hooray for geometry.